Topic of this video is clocked RS flip-flop. But before we begin, we must first understand this concept of synchronous and asynchronous sequential circuit. Now this we have done earlier also. We'll quickly look at it. So synchronous sequential circuit means that it is synchronous, meaning there is a time signal. That means it must have a clock signal associated with the inputs. That means output changes at discrete interval of time. It is a circuit which is based on equal state or state time, depends on the state time, and which is defined by external means, and external means here is the clock. Later we'll call it as clock pulse. Okay, so if in the circuit you have clock pulse, it is called synchronous. That means according to the clock signal the output will come out. Whereas in asynchronous, in simple words, we'll say that there is no clock pulse present. Okay, the result, the output will get depending on the combination of the inputs. Okay, not and there's no clock associated, and because there is no clock associated, no timing signal, that is why it is called asynchronous. So in synchronous we have clock signal CP, whereas asynchronous it's purely based on the combination of the input and no timing signal present. So now we'll look at the circuit diagram of the clocked RS flip-flop. So here is the clocked RS flip-flop, which is similar to our SR flip-flop. Now in SR flip-flop, if you remember, we in the truth table, we encountered a problem of having invalid state. Here also you'll see invalid. Okay, so this was the problem earlier, and so to overcome that, we have little modification here. And if you look carefully, you'll see that this part is extended. And this part is extended, meaning there is this input called clock pulse is added. And that is why we say that now it is a synchronous circuit. Okay. Now synchronous, why? Because it has a clock pulse. And with the help of clock pulse, we can enable and disable the circuit. So and we can time it. Okay, we can then according to the timing of the clock's pulse, we can get the output. Okay, so this is the difference. Clock is introduced, and because clock is introduced to overcome the invalid state, it is called clocked SR flip-flop, and you have to add this clock. And so if you look carefully, this clock is combined with the R. Remember reset. Okay, reset and set. So reset input, it is ANDed, this AND gate, and with S also it is ANDed together. Okay, so so the clock will now control the output, and clock will be enabled when clock is equal to 1. So if it is equal to 1, then only output will depend on R and S. But if it is equal to 0, then because of AND, any other value, whatever is the other value, if clock is 0, then 0 will come out. So that way clock is controlling the signals. Okay, so this clock can enable and disable the circuit. So let us quickly now try and understand the truth table. Out here we will see that the columns have changed slightly. So here we have S and R, no doubt, and then we have QT. QT here is our previous. Remember, we have to also consider the previous value, so we are making a separate column for that. That is denoted by QT. And so that is your Q previous, and the result that we get at present, that is your QT new. So it is denoted by QT plus 1. Okay, so the columns are like this now. And also we have to understand that this truth table will be enabled as long as CP is equal to 1. If CP is 0, that means no matter what value here, this circuit will be not able, it will be disabled. Okay, so let's quickly go in. So first of all, we will take S and R as 0. Okay, before we begin, also we have to understand that our previous we have to assume now the previous Q value. Okay, what was the previous? So first of all, we'll assume that it was 0, and with that 0, these combinations. So 0 0, all that. And then next, after we have taken all the combination, then we have to assume that QT was 1, and again the values. Okay, so that is why you'll see here 4 zeros with 4 combination and 4 ones. So this is your QT previous. All right, so let us begin. So when QT is 0 and RNS is also 0. Okay, 0 0. Now for this, if you remember in our RS truth table, which I have here, if you look carefully, whenever we have cases like this, RS 0, Here also two cases we have seen earlier. We get the same previous value. Okay, so we get the same previous value. So here also we'll take that into consideration, and we will keep it as because it is 0 0 and my previous is 0, so we'll keep it as 0. That is why I have written here also same as previous, because already previous is 0, so we'll put that as 0. Okay, and the next row. So Q2 is 0. Here S and R, R has changed. R has now become equal to 1. And again here I would repeat, whenever you have in an OR gate, your one of the input is 1. Okay, I'll show you also. It is here the pattern that we have to always remember. It is there in your previous video also. Okay, so it says that in the NOR gate, if any one input is 1, then the result will be 0, then output is 0. So that pattern again will we have to remember. Okay, so here that pattern 1 value, so we'll go for that. Where is my R? R is here 1. Okay, so 1 will come out, so here it will be 1. So no matter what, if there is 1, then Q will be what does the pattern say? Okay, that it has to be equal to 0. Okay, look here, it has to be equal to 0. So here, remember, this pattern is very important. It was important earlier also, this time also it is important that if any, that's why I'm repeating it again, that if any input is 1, then output is 0. So we'll make use of that here also. So if any input is 1, so if this is 1, it will be 0. So straight away we will write Q as 0. My new Q is equal to 0. Okay, so now the third one, again Qt we keep it as 0. Then this time we are making S as 1. So S as 1 meaning this will become 1. And no matter what, if this is 1, one of the input is 1, and what does the pattern say? That Q prime will be equal to 0. Okay, so Q prime is equal to 0 meaning Q will be 1, complement of that. So Q will be 1. Okay, this step is very important. It has to be clear. So this is called set. From 0 it has become 1, so it is a set state. Now as I told you, clock flip-flop changed to from RS we changed to clock SR flip-flop to overcome the next combination, which is your 1 1, which resulted in the invalid state. Again, I'll show you the previous one. So here the last one, see, if it is 1 1, then it resulted in invalid. So that is overcome, not overcome, but it is handled in a different manner. Okay, so here also both are 1. So if both is 1, then both should be equal to both is equal to 1 1. Okay, so that we no longer call it as invalid, but we call it as indeterminate. Okay, because the presence of the clock pulse is there, so that will handle the problem now. Okay, so the occurrence, now we have the clock pulse along with this values. We say that the occurrence of clock pulse causes both outputs to momentarily go to 0 and not invalid. When the pulse is removed, the state of the flip-flop is indeterminate. That is, either it can be 1 or it can be 0, but not invalid. Okay, so now we no longer consider it as invalid, but indeterminate. Why? Because of the presence of the clock pulse. Okay, so that is how that invalid problem is taken care of. Okay, so now here, after indeterminate case, then the value of clock will change. Okay, and then our QT previous, all the 4 values are done. Then we go to the new set of QT, where QT is previous is 1. No more it is 0, but 1. Now we work out with all the combination. Okay, so 1. So again we come across this case 0 0. So whenever it is 0 0, what happens to the output? It is same as previous. All right, so this was our previous to invalid. In indeterminate we have 1, so we'll keep that as 1. Okay, so it's same as previous. Then coming now to the next value, here now S is 0, R is 1. Okay, so we'll again go to this one part and apply that pattern. So R is 1. Okay, R is 1 meaning if this is 1, this will be 0 following that pattern. Okay, so Q is 0. So here it is 0. Okay, I hope it is clear now, the pattern. All right, the next is again SR. Now this time S is 1. So we go down here 1. This is 1. Okay, so if this is 1, no matter what the other input is, If this is 1, it will be 0. Now q prime is 0, meaning q will be equal to 1, which is what is the case. Okay, and then again, same case, 1, 1. That is when we encounter invalid. Now it is no longer invalid. It is now called indeterminate. It can be either set or reset. So this is how the truth table changes when we introduce the clock pulse. Okay, and no longer we have to face this invalid problem. Okay, we overcome the problem of invalid combination with the help of introduction of clock pulse. Now here, if you look here, okay, these are the combinations. Now from these combination, if you remember Karnaugh map, in clock RS flip-flop, whenever they ask you the question, you also have to draw the Karnaugh map besides drawing the truth table. So I hope truth table is clear. Now I'll be explaining the Karnaugh. Okay, for the Karnaugh map, first of all, we'll draw the structure. Now because 3 variables are there, Q, S and R, so we have a 3 variable Karnaugh map. Okay, and I hope you remember these combinations. 0, 0. For S and R is 0, 0, 0, 1, 1, 1 and 1, 0. And this side is Q, 0 and 1. Okay, so now let us look at the, from this truth table, how we are going to fill. So we will mark those rows where the value of Q is equal. Qt plus 1 is equal to 1. So we have 1, 2, 3. Okay, 3 values here where it is equal to 1. Okay, so first of all, this one. So what is the combination here? 0, 1, 0. So look for that. 0, 1. Look carefully. 0, 1, 0. So I'm writing here 1. Okay, that is my first one that goes in the Karnaugh map. Then next it is 1, 0, 0. So search for that. 1, 0, 0. So here it is. One more one. Okay, my second one. And then my third one. My third one is this 1, 1, 0, which happens to be here 1, 1, 0 here. Okay, so altogether 3. Plus one more thing. We have these indeterminate state. So it can be either equal to 1 or 0. It may be equal to 1. So now that it's like a don't care condition. Okay, so we put those values here as my, here I have made this green cross. So these are your don't care conditions. These are actually depicting the indeterminate state. Okay, so here it is. One is your 0, 1, 1 and the other one is 1, 1, 1. So which is where you'll find these two. Okay, so altogether 5. So I will not go very much inside the Karnaugh. You already have the concept. Okay, so I'm combining. So there's two combination possible. One is this green rectangle. So all these adjacent values are wrapped in that, this green rectangle. And the other one is this blue dot. If you can see this one coming till here. Okay, so that is how we pair up, do the pairing, two combinations. And now we have to find the terms. So from this green box, if you see, what is the variable that is fixed? So look carefully, this the first one is fixed. So that is actually your S. Okay, so the variable that is fixed, we have to jot it down. So from the green, we are getting S. And from this blue dot, this one and this one here, if you check carefully, the value of Q, because both are in the second row, Q is not changing. And your R prime is also not, the first one is also not changing. Okay, so we will, I hope you know the process to list all the constant variables which are not changing. So in this green one, S is not changing. In the blue one, Q, R prime is not changing. So we put it together and that is the expression of our truth table. Truth table for expression for our clocked SR flip-flop. Okay, so I hope it is clear. Okay, my SR flip-flop and clocked SR flip-flop. Very important, you have to know how we generate the truth table, and in case of clocked, how along with the truth table we also have to know how to draw this Karnaugh map and the expression. Very important expression. Okay, thank you.